Okay. If you can see my screen. Can you see my screen?
Yes.
Okay. Should I start or should I wait 1 or 2 minutes?
You can start. I think
Okay.
there are 20 participants.
Okay. Good morning, good afternoon, everybody. So I want to talk about some recent results we achieved in our group using some quite some computing power, facilitating a praise call. Praise is like a way to get in Europe like large amount of computing resources. So they have every, I think, 2 times a year call. So yeah, so use these resources to actually do quite high global convective dynamo simulation. So one example is here in the background, and to want to investigate how this large scale and the small scale dynamos are interacting, or how they interplay. Yes, just a general overview. So if you talk with about solar and stellar dynamos, so you know all the butterfly diagrams. I probably don't have to explain that. You see here the appearance, or here the coverage of the active region, the sunspots, as a function of time and latitude, and you get this very nice pattern, which is called the butterfly. So that's the butterfly diagram, and this is normally associated with the large scale dynamo, which is the differential rotation here on the left here from the sun is one important ingredient, and the other ingredient would be turbulent convective motion influenced by the rotation, so the alpha effect, for example, or other turbulent effects. But additionally, you can have a small scale dynamo. A small scale dynamo action, there important is that the peak of the magnetic energy scale is normally smaller than the driving scale. And in contrast, for example, to the large scale or mean field dynamo, is that no real large scale rotation or large scale shear is needed to excite it. And for example, why is this important in the sun and solar like stars or other cool stars? You can provide actually small scale magnetic field on equipartition strength through these effects. So the small scale dynamo important is in the sun. What I would try to talk about a bit about the interaction between the large scale and small scale dynamo. How do they interfere each other? You can have, for example, because of this large small scale fields, you can have quenching of convective flows. You can have influence on the angular momentum transport in this in the sun and the stars. And for example, when you talk about the surface, it can also, when you have very equipartition small scale magnetic field, this can also influence how the energy is provided to the corona, and that's why heat to corona. So normally it's actually the small scale dynamo is more difficult to excite than the large scale dynamo, because the critical Reynolds number is normally much higher. So it means to have both excited in such a global convective dynamo simulation normally need quite high resolution. I come to that, how high you need, or at least what we find. So maybe just to a few cases where this have been studied before. As I said, because it's very difficult to excite both at the same time in these global settings, there haven't been actually so many studies about it. So one quite interesting and famous study is the one by Hideyuki Hotta, who already quite early on pushed the resolution of his models quite high. So what you see here is he has, in this paper, it's a science paper, he has cases of with 3 different resolutions, so low resolution, medium resolution, and high resolution. And he sees that that the large magnetic field first becomes weak and not really so cyclic anymore, and then he retrieves it after reaching a high resolution. And his interpretation, that's a quote of his paper from his abstract. He said, "We found an efficient small-scale dynamo in this high case, that suppresses small-scale flows which mimic the properties of large diffusivity. As a result, the global scale magnetic field is maintained even in the regime of small diffusivities. That is large Reynolds numbers. So it means, he said, it's, in his interpretation, it's quite crucial to have the efficient small-scale dynamo to retrieve such a pattern. Another important study was the one where Petri Kepler was the lead author, was also part of it. He did a study also where he pushed the magnetic Reynolds number quite high to, I think, 130, 140. And he actually sees, so that's the measurement of the radial differentiation and the latitudinal differentiation. And he actually sees that the shear, so the differentiation becomes highly suppressed when you have a high magnetic Reynolds number, and you have, in some of these runs, even also there, very efficient small-scale dynamo. And quite recently, there have been a paper by Hideyuki Hotta, who claims that in his paper, he has also studied with low resolution to high resolution, that because you have a very efficient small-scale dynamo, your dynamo actually, or your differentiation change from anti-solar, what is here, to solar-like differentiation. Anti-solar means that the equator is actually rotation slower than the poles, other than the sun, where the equator rotates faster than the poles. So, so that's just to set the scene, okay? So it's a very interesting problem to study. So what we do is we take one of our, I would say, typical global convective dynamo simulation with the pencil code. Here's one example where you have a butterfly diagram, which looks a bit similar to the sun. You have a differentiation, which have these nose features, which seem to have been quite famous now, and a multicellular circular mirror circulation. And we do a wedge simulation, so we only take a quarter of a sphere to actually can push the resolution higher. So, and here, overview of the equation we solve. So we solve the induction equation, the density, the continuum equation, which solved the momentum equation here with the Coriolis force and the Lorentz force, for example, to mention. Then we solve the energy equation in terms of the entropy with the different heating terms, so ohmic heating and viscous heating. And then we have the different heat fluxes. So there's the radiated heat conductivity and heat conductivity by what we call the SGS, subgrid scale modeling. So we just have a isotropic turbulent diffusivity to transport out the flux. I can come to, if you have questions to it, I can explain in detail. Important is that we use, since a few years now, for the radiative heat flux, we use radiative heat conductivity, which follows based on the Kramer's opacity, so that you have a dependent on the local temperature and local density this way, which can lead to it that you get different dynamical layers, and that basically the size of the convection zone is self-consistent, chosen by the simulation. And on the top, we use a black body boundary condition. Yeah, good. So just to get you away how we do it. So this here the different runs. So O is here the run what I showed before. So that's our standard run, standard resolution. And then maybe basically when you go down, so the numbers increases, you actually increase, so we lower the diffusivity, so the magnetic diffusivity and viscosity and the SGS turbulent diffusivity. So it means that the Reynolds number, so magnetic frontal number is 1, so fluid Reynolds number, magnetic Reynolds number the same, so we push it up to 500. But you need a resolution of 2000 times 4000 times 2000 to reach it. Yes, so the Coriolis number is roughly the same, so the actual rotation It's the same for all of the runs, so it's basically just a study of different diffusivities. Also, yeah, so we need to actually, what is shown here is that for the high resolution runs, we need to increase the diffusivities near the latitudinal boundaries, because there's sometimes some weird things happen, so we increase it there quite narrowly near the boundaries to get it more stable. And we use actually the slope limit diffusion in some hydro runs. So as you see here, there are different types of runs. So there's M and S and H. So M is basically solving the full MHD. H is just the hydro cases, so no magnetic field. And S is a special case. So we have for every case, what we do, we want to know if there's really a small scale dynamo there or not. How we do it, there's a way in the pencil code that you can in every time step suppress or remove the mean field, so the m equals 0 mode, so the actual mean field, and this means that a no mean field dynamo actually exists. And if you then see that the magnetic fields still saturate to a different level and doesn't decay anymore, we know there's a small scale dynamo. So, and what we see here is these are these runs where we have suppressed the large scale field. So this is with the S showing here. And yeah, what you see is that you actually need to have a efficient small scale dynamo. In this setup, you need a Reynolds number of roughly 140 to get excited in these cases. Okay, good. So these are the runs. So let's look at certain properties. So first of all, one of the highest resolution, a movie of it where you show in the background the full radial flow close to the surface, and here this is a cut basically of zoomed in region where you see this actually nice convection cells with the elongated, which is normally called banana cells, which is also expected from basically at such a rotation. So the rotation is a bit higher than what is expected for the sun. Yes, and if you now look at the corresponding radiomagnetic field on the right-hand side, then you see this. You have quite nice field concentrations.
John, Kuba has a question.
Yeah.
Jörn, can I ask a quick one? I've seen these movies many times, long time back, and never occurred to me. Is the banana cells, does it seem like they're going on a wave around the equator?
Yes.
I see. Interesting.
Actually, there's a theory. We didn't look at this. That normally you can interpret the banana cells as thermal Rossby waves, and they have their own pattern.
Sorry, what waves?
Thermal Rossby waves.
Thermal Rossby waves. Okay, interesting. Okay, good, excellent. Thank you.
They have it's expected also to have their own pattern speed. Also in the sun. There's also some observational work on this.
Sun is too difficult. I just care about simulations.
Good. So yeah, you see very nicely that that you get these nice also local flux concentration. So just to illustrate also how these what I call the artificial suppression of the large scale magnetic field works. It's like this. You see on the top the corresponding runs, so 2M, 3M, and 4M are the corresponding MHD runs, and then in the lower part is the corresponding runs where we suppress the magnetic field. So this is basically the field. Now we see here the toroidal field, or the azimuthal field, better to say, just generated by the small scale magnetic field. And you see that you see normally here these bands, and they are completely removed as expected, and this is quite some small scale magnetic field. Yes. So now we can look at the energy as a function of Reynolds number. So on the top is the flow energies, the fluid energy, and what we actually see is, so now I show some many similar plots. So the solid lines are always the MHD runs, the dashed ones, so like these ones here are the hydrons, and the dotted ones are just the ones with the small scale dynamo. And what you see here is that the hydrons normally have a larger differentiation, so which is highly quenched when you have a magnetic field. For example, that's one point. The other point is that the turbulent flow slightly, so the fluctuation of the kinetic energy slightly increases with Reynolds number, so it's not seem to be not affected by the magnetic field and the small scale dynamo. And the mirror circulation, mirror flow is always weak. And I think that's also an interesting point, because it has been always claimed that why in the simulation the mirror circulation is so weak and is not important for your dynamo. But this is related maybe to the Reynolds number, but we see even if you push the Reynolds number very high up, the mirror circulation is always weak. So then when you look now at the magnetic field, so the black one is the total magnetic field and the red one is the fluctuating magnetic field, then you see you have an increase of the small scale magnetic field, which leads to increase of the total magnetic field, and the dotted one is basically the corresponding runs with the small scale dynamo alone. So, for example, for this Reynolds number is pretty weak yet, but then in the end they become comparable. So the fluctuating magnetic field from the small scale dynamo and from the large scale dynamo, so the tangling, are basically comparable. And what is also interesting is that actually the large scale magnetic field seem to saturate. So there seem to be even here a small decrease. Just forget about here the other points. So it's increase, and interesting also the field becomes more toroidal. So the blue one is the toroidal field and the purple one is the poloidal field. So the higher you go with the Reynolds number, you become more toroidal. This you can, for example, now compare with earlier work by Petri et al., where he actually looked at different codes, different other simulation. So in the blue one is, for example, the one by Hideyuki Hotta, and the red one is by one simulation from Nelson from the Ash code. And there you also see that the total magnetic field increases. That's all consistent, what we see here, but that the mean magnetic field seems to also saturate, which we see here. And we don't see anything like this, what Hotta proposed, that it first goes down and then up again. So we don't see, maybe here's something, but not as strongly as this. So then interesting is see what is actually happening to the turbulent flow. So the small scale velocities here is a function of radius for all these runs. And there you actually see that when you look at the solid line, that you have an increase with Reynolds number and then a slight saturation. So these are the hydro runs, they actually show a more stronger increase. And this is a comparison to the Hideyuki Hotta's very recent results, where he claimed actually with a very efficient small scale dynamo, he see actually a strong decrease of the UMS. So we don't see anything like this. And that might be related to that the setups are a bit different and that he uses a certain, particular boundaries conditions which might lead to what he sees. And of course, he used the slope limit diffusion. There we also don't know what effect this might put on it. The other important thing is that we can look at the turbulent magnetic field. So you see that it increases the more you go to 4 is the highest resolution. So you see that you have this, but actually we don't see very strong super equipetition fields here, for example. So only very weakly here. So so that's the question also why Hideyuki Hotta, for example, sees, or other people sees when they use slope limit diffusion in convection, why they actually see this very strong super equipetition fields, and but we don't seem to see it. So when you now look at the spectra, you can see here this is the kinetic spectra, you see you get a very nice inertial range following this 11/5 law minus the 5th law. So this is this, I hope I pronounce this correctly, the Bulyanov-Ubukov spectrum. But for the magnetic field, what you see at the bottom, you don't really see any inertial range. So there's not much what can basically fit any power law. If you take the ratio of both, you see again that you only get very weak super-equipotential fields. Yeah. Okay, so then one important thing is what I told you before, that you have this, we use the Kramer's opacity or the Kramer's, the heat conductivity follows the Kramer's opacity. And then you can have some different dynamical layers. What I mean by this is that you have normally a typical convection zone, but if you use, what do you say, yeah, this Kramer's opacity, for example, you can have the build up of different other zones. So how they are defined, so this is a paper by Petrie, a different one from the same year, where you actually see that when you are, so depending if you're convectively stable or not, and if you have a convective flux, convective flux. So you have the buoyancy zone, so the typical convection zone, where you have actually a positive convective flux, and your Schwarzschild criterion will tell you that you're convectively unstable. Then you have a zone called the Dierdoff zone, where you have still a positive convective flux, but your Schwarzschild criteria will tell you you're convectively stable. And then you have another zone, which is basically just the overshoot. That is clear, where you have a negative convective flux, and the radiative zone where the convective flux is pretty weak. So now we can look at these layers also in the convective zones in these global convection simulation. I have indicated with colors. So the buoyancy zone, so the the old convection zone is in yellow, the Dierdoff zone in red, and the overshoot in green, and the radiative zone is in black. So what you see actually here over, so when you go to the right, you go to higher magnetic Reynolds number. It seems like you have for the lower part a quite extended Dierdoff layer, which then becomes smaller. And then what you also see, it seems like that the radiative zone, so that's a bit noisy, but the radiative zone becomes actually stronger. Otherwise, there's not a super strong dependency. There's some difference between the hydro run and the magnetic runs. This is also because you have in the magnetic runs, sometimes magnetic field stronger in one hemisphere than the other. And that's why this also you see this, hemispheric variation of this layer. So now I'll go a bit faster through it. So now one part is the differentiation. It's a bit complicated to see, but important is that the differentiation actually becomes smaller when you go to higher magnetic Reynolds number or fluid Reynolds number. And this nose, what you see sometimes here, is actually vanishing, which might be important later for the magnetic field evolution. So now one important thing is, so why does the differentiation changes? So now I try to give you some idea what can happen. So for this, I look at the different contribution in the, or the main contribution for the angular momentum. And this is related to the stresses. So one is the Reynolds stresses, what you see here. Then it's the small scale Maxwell stresses, so from the small scale magnetic field, and the large scale Maxwell stresses, which is related to the large scale magnetic field. And all together, they become basically the total stresses, which then actually are put into the angular momentum transport equation. Just to illustrate how the magnetic field can actually change the whole stress tensor, you can even look at the 0, 1, which is actually the low, even still the low Reynolds number. So the dash one is again the hydro case. So you see the black dash one, and you should compare it first. So this is basically the Reynolds stresses from the hydro one, which is the total stress, it's the same, compared to the blue one, which is the Reynolds stresses from the magnetic field run. And you see that it's already have changed quite a bit. So it's already become much weaker and even a changed sign here. And then additionally, you have in the magnetic field run, you have the two Maxwell stresses, and together they really change completely the picture. So if you compare now the two black lines here, you see that, for example, here at high latitudes, the Maxwell stresses have completely opposite sign. And then you can imagine that this will, of course, influence also your differentiation. The things when you go to higher resolution becomes more and more complicated, as you would see here in the lines. And but we can summarize that it's really that the magnetic field has a very strong influence on the Maxwell stresses. Of course, you have to see that that this is only in the saturated state. It's important, of course, what happened when the differentiation are building up. But yeah, that's the best we can do. So one interesting part is also that you can look at the current helicities. So even it's written here H mark, I mean actually the current helicities, so which are maybe related to the alpha quenching. And then you can see that here the magnetic field runs and here the small scale dynamo runs. You actually see that the current helicity is actually opposite when it's just generated by the small scale dynamo. And I think that's quite interesting. I don't know if someone like Axel would have expected this, that the current helicity is actually different. So now
you have 5 minutes.
5 minutes. Oh, okay. So now coming to the magnetic field evolution. So now you see here the typical butterfly diagram. So the toroidal field near the surface, that's the toroidal field at the closer near to the bottom of the domain, and that's basically a cut at here certain latitudes and showing as basically time radius. So and you see that as I said before, the M0 is basically our typical simulation. And what we already see there, you see this nice equatorward migration pattern near the surface. When you go deeper down, you actually see the different dynamo mode, which have been investigated quite thoroughly by Maria Kepler in the so-called Millennium simulation, which is basically exactly this simulation without Kramers. And you see that this happens. So when you now go to different Reynolds number, that this or higher Reynolds number, so when I go down, you see actually that the pattern, the equatorward migration pattern actually vanishes, but actually this pattern, what you have here at the bottom, still remains. And it seemed to be, when you compare these two plots, you see that they are very similar. So you see very nicely that's actually at the bottom of the domain. So we seem to have that, except of the vanishing of the equation pattern, it seems like actually that the overall dynamo pattern doesn't really change much when you go to much higher Reynolds numbers. Yeah, let me then first say also some other things is, and now you can also look at how the differentiation probably quenches over time. And I just want to highlight, so this is a similar plot as before, but just for the omega. What you can see actually here and here is near the surface that you have phases where actually the differentiation have shifted from solar-like to anti-solar-like, like temporarily. And I think that's quite interesting that the magnetic field is so strong to changes the differentiation that strongly. Okay. Oops. So now coming to the conclusion. So this is the first overview of some results. We're still doing some more further studies. So we have pushing the magnetic Reynolds numbers to up to 500 to have a really efficient small scale dynamo. We see that the differential equation is highly quenched by the large scale dynamo and small scale dynamo. So it's not that just you need a small scale dynamo. It's already enough that you have a large scale dynamo, and because you have high Reynolds number, you have the tangling, so very strong small scale field by the large scale dynamo, which can quench the differentiation. We see that the turbulent flow actually increases with magnetic Reynolds number and then saturates, so we don't see a decrease. We don't see any very strong superequation small scale field. We see that the dynamic layers, so the Dieldorf layer and stuff, are a bit influenced, but not really strongly by increasing the Reynolds number. We see very important that the magnetic contribution to the stresses play an important role. And somehow surprisingly, is that large scale mean magnetic field evolution does not change much when you increase the Reynolds number. Yes, and as I said, locally you can have actually the differentiation change from solar-like to anti-solar. So we are currently also running for all these runs basically the test field setup, so we can actually also look at the coefficients. Of course, we have to see how the method, how valid it is in terms when you have an efficient small-scale dynamo. But the first interesting test revealed that that actually the coefficients are not really changing much when you go to much higher magnetic Reynolds. So we, I think, say now that you have the loss of the nose explains why you don't have a equator ward migration anymore in the higher Reynolds number runs, but the rest seem to be really the same. Okay, thank you a lot.
Thanks, Jörn, for the interesting talk. Now, okay, I see two right hands. Dhruva, you can ask her.
It was raised previously.
Oh, okay, Axel.
Maybe he had just a hand open.
Yeah.
Sorry, my mistake. That's just the old hand being raised.
Axel, you can ask.
Yeah, thanks for Jörn. Very, very interesting material, new material you have and findings. So your simulations are not then with slope limited diffusion.
No.
And the magnetic. So now the question is, first of all, the magnetic Prandtl number. What have you? It's one. So, so you see these horizontal structures. If you look at these banana cells, they're connected with these horizontal structures, right? Yes, exactly, which I remember Petri found at one point and was not, in the beginning wasn't sure whether there's some something really wrong or something, because they require all of a sudden much higher resolution, you found back then.
Yes.
So
yes,
now
so you see sometimes these you see this in this one or in other ones, you see sometimes very strongly small scale turbulence near the equator that you find. But this, I mean, interestingly, when you use, it seemed to be if you use the Kramer's heat conductivity, these runs are run more stable than if you use the old school heat conductivity. So I use only at the what do you say, at the latitudinal boundaries a bit higher diffusivity, and I use only in some of the hydro runs, I use the slope limit diffusion on the flow.
So when you then use Kramer's opacity, does that actually mean that the magnetic, that the fluid Prandtl number is potentially even large?
Yeah.
Or is it actually, you think it is actually large, right? Not small.
Yeah. So the Prandtl number according to the SGS is always 1, so that we lower also. So, but the Prandtl number, if you add, that's now estimated from a 1D model, but it gives you a good idea at least. So it means that the Prandtl number actually goes down.
Yeah, yeah. Oh, it does go down.
Actually, that the you can also say like this, that the Kramer's become more, the Kramer's heat connectivity become more and more important.
Yes, because that one is not changing with your. Exactly. I mean, you don't have a Peckley number, which is adapted to the increasing resolution. So you basically make nu smaller. as you increase the resolution, and don't change the opacity.
Eta and chi t smaller.
Yeah.
But
Yes.
the framers,
So are
prefactor
you
stays
thinking?
the same, yes.
Do you then think that these horizontal structures are actually a specific feature of low magnetic Prandtl number rather than high? So they would become even more pronounced if one has smaller fluid Prandtl numbers.
I mean, we actually don't see a large difference. So a large difference in these bananas. Do you mean the banana cells or what?
Yeah, these horizontal structures in particular, these small scale turbulent ones.
They become more pronounced when you go to higher resolution. I don't know, because
so
yeah.
So it looks like it's a special feature then indeed of low Prandtl numbers, which is good. I mean, or interesting. And now another question.
It's really this, because we changed other things also. So it's it would be then more important to what do you say? Only change the fluid Prandtl.
Yes. Yeah, maybe so. Okay. Could you then also give us an update on the status of slope limited diffusion? What is it was said during the meeting here that it wasn't working for the magnetic field, but for the fluid it was working. I mean, so what is the status?
So I would say it is. Technically, it's working also mostly for the magnetic field. Yes. At least in the Cartesian runs, it seemed to work normally, maybe as you expected, I would say. For the spherical runs, it also, that's actually, it also runs fine. So the difficulties I think I had, when was it, a year ago, was to do that in these runs, because we're using this very high luminosity. Our Mach number is pretty strong. The local Mach numbers are pretty strong near the surface. That's why you have to make some prefactors to your characteristic speeds, or use a certain profile, and then it also works not bad. But on the other hand, that I give, I think some days ago, some update, is that if you use the slope limit diffusion, you have to be very careful with your parameters, because you can get dynamos in 2D and stuff, and dynamos from irrotational forcing. If you choose your nonlinear parameter too strongly, at least in our implementation. I can show you. You can look at my.
So maybe what we should do is we should resume on that one during one of the coding sessions, if you have time.
Yeah. We have coding session just after this. We can continue there.
Yeah.
Jörn, very impressive high resolution simulations. Thank you. And I think Axel did ask the question, but I'm not sure. So these banana cells on the sun are actually elusive. I mean, you don't see them normally. So do you see that when you increase the resolution, this banana cells become fainter or less obvious, or?
Not so much. I mean, that's the highest resolution. And you don't see the difference. So what makes, of course, the difference into the sun is that, so there are two issues. One is that this is a slightly higher rotation, or is higher rotation. So maybe a factor of 3 to 5 larger.
Okay.
Depends what comparison you use. So that's why you expect to have here more stronger banana cells. On the other hand, I look at, for example, the scale of these banana cells, the peak scale, if this actually changes with this Reynolds number, and it does not. So it seemed to be rather constant. So that is also expected, because it should be at least the wave number of this wave should be related just to the I think rotation, and not through
what basically you're concluding is that the small scale dynamo is not affecting your large scale dynamo,
Yes.
as or as other people, for example, Kota and
Yeah.
all.
I wouldn't say. I mean, we were actually surprised that the effect. I mean, there is an effect as I showed on the differentiation, which explain you basically. I would say explain you the difference between OM and 1M. So this is because the differentiation doesn't have this so-called nose anymore. So that's why you don't have the equator word migration anymore. But otherwise, I would say it's not really so strongly dependent on it.
And these simulations don't have a tachocline, right? It is just.
They don't have a tachocline. But you have to also say that the problem is that, so this is now 3M is not the highest resolution, and already this we can't run so long because it's super expensive. So it's very hard, of course, compare these runs with these ones. And even the very highest resolution, you could only run very short. So never had their cycle. So there, of course, extrapolating to this level, it's very difficult. But we don't see that we see that somehow the large scale fields seem to saturate, but we don't see there's a very strong influence of the small scale dynamo on the large scale field at the moment.
Thank you.
Yeah, thanks, Jörn.